So what I want to talk about today is how to scale artificial intelligence and data analytics. And I really want to answer or address two questions. Can deep learning be done on Spark with GPU acceleration? And also, can data analytics and machine learning be done on dense GPU nodes? And so if you're doing data analytics or machine learning, traditionally Spark is an exciting and superb platform for that. It allows you to program in different languages that people like, Java, Python, Scala, R. And of course, the important thing is that you can scale out and you can pull data seamlessly from a Hadoop cluster, all that great stuff. On the other hand, when deep learning sort of exploded in the last 5 years in 2012, GPUs became very critical because they're extremely compute intensive in the algorithms, backpropagation. I'm assuming we all know something about that and the motivation to do deep learning. But when it did explode, what happened is NVIDIA GPUs became extremely critical, and we wrote a set of libraries that allowed to harness the computational power of NVIDIA GPUs for deep learning. And very quickly, those libraries were tapped into by the deep learning frameworks. And so even just one NVIDIA GPU would accelerate deep learning in a very important, meaningful way. But what we did recently is we started to build custom hardware like this DGX1 box that I'll talk a little bit about for accelerating deep learning. Now, let me motivate a little bit why you need a box like this, which has 8 NVIDIA GPUs in it, and talk a little bit about how distributed deep learning is done. So what's called data parallel distributed deep learning, the way that it's done is you have a deep learning model and you have a master parameter server. What you do is that you take replicas of that model and you put them on n different workers and you shard the data into n different subsets that are disjoint, and you feed these data shards in mini batches to the workers, and what they do is they train the model in parallel, and then at some point you average the parameters. You basically send the parameters back to the server, it averages them, and then it sends updates, and it updates all the models. This can be done synchronously, or there are ways of doing it asynchronously so that the different workers don't have to wait for them all to basically be updated. And so because GPUs are so much faster at training these models and doing backpropagation algorithms, GPU compute becomes extremely important. And what you'll notice from this is often this can be tens or hundreds of terabytes of data, even more in some cases. You typically end up with a very dense compute node. So a lot of GPU power in a single box, for example, with relatively little memory. Because as long as you can take the data, which is typically unstructured data like images, and feed it to it fast enough, it doesn't have to be permanently resident in memory. And typically you wouldn't want to necessarily have that data filling hundreds of terabytes of memory. So it's a streaming process. And so you end up, and again, the GPU performance over the last decade or so has scaled both in compute power and peak memory bandwidth much faster than CPUs, which have basically stopped scaling in single-threaded performance because of Moore's law. And so this led us to create this very dense compute box called the DGX1, and it basically has 8 of our latest GPUs connected with a very fast interconnect mesh called NVLink that's much faster than PCIe. And we've worked very hard to make sure that we can containerize all the frameworks in Ubuntu, and you can pull them down from a softed software registry, and that they all run perfectly on this box. And you can see that this DGX1 box is faster than 128 Knights Landing servers on a typical deep learning benchmark like AlexNet. And so the bottom line is, well, if this box is faster than 128 servers, what would happen if you linked with proper fiber optic connections 128 of these DGX1s together? Turns out that you would get the 26th most powerful supercomputer on the top 500 list, and you would only need 13 DGX1s to get into the top of 500. So the ability to scale out compute for deep learning in these dense nodes is established. And a lot of the big cloud service providers that do a lot of deep learning are using these. But the question that we really want to address is, so the scaled GPU deep learning is covered. People are doing that. But the question mark here is, what about Spark? What if in this scale out and scale up diagram, so scale up means that in a node you add GPUs. What if you take Spark and in the nodes you add some GPUs to it, maybe not 8 per node, but can you do deep learning on Spark? That's the question. And so typically we talk about artificial intelligence and deep learning as really being a new paradigm for big data. Traditional data analytics, things that you would do with Spark or a proprietary architecture, you often talk about a Lambda architecture, so you have a streaming and a batch processing branch, and you're doing historical data analytics, where on the big data that you store, let's say in your Hadoop data lake. Whereas with deep learning, you've got big data, you're constantly training and deploying models, and they're getting better and better, so it's this sort of a virtuous cycle. And the question is, can you do deep learning on Spark is the first question I want to address. And so this slide is a courtesy of Tim Hunter from Databricks. And basically, there are 3 approaches that are being used. There's using deep learning frameworks with Spark bindings. So the idea is that you have the data that you want to train on in deep learning in a Spark data frame. And in that Spark data frame, you have a binding to something like TensorFlow or MXNet. But the problem is that's not very efficient because you have the memory in a Spark data frame, and there's a lot of speed lost in the translation in pulling in the data. So what some of the other approaches do that Tim here is calling native Spark is they're actually tightly integrated with Spark. And so one of the frameworks that I want to show you that I think does a fantastic job of that and talk about specifically is a deep learning for J, which is SkyMind is the enterprise version of the framework Deep Learning for J, which is a framework that you can interface via Java, and they have a Python interface coming. But what it does is it takes this scheme that I told you about, so you can shard the data from a Hadoop cluster, you can pull it up into Spark, and have your data shards actually initially in the Spark data frame. But what it does is it'll set up a job for deep learning where it takes the shards of data off heap. So they're not on the JVM heap. They're pinned in memory that it reserves. And then it launches jobs on the GPUs that are resident, let's say, in your Spark workers. And it takes control. And it will do that training process very, very efficiently. And then when you get your results, you can put them back into Spark, or you can take them into another system. And so we think that SkyMind and Deep Learning for J has really done a fantastic job, because what they do is they integrate into the whole ecosystem, and they allow you to construct the whole workflow. So they allow you to do this integration with Spark, to use your Spark applications, have GPUs, pull up data, like I said, pin it off heap, and do your training, and they have all the usual things that you'd want. They can stream from a Kafka and Storm. They can do vectorization to do the data munging that we all take so much time. And so I think they've really done a great job of that. Another interesting implementation that can at least pull data from Spark data frames is H2O's Deep Water. So H2O is an enterprise machine learning and deep learning platform that's open source, and it has paid enterprise versions. But the version called Deep Water, what it can do is it can, if you have GPUs present on a cluster, it can use the popular deep learning frameworks such as TensorFlow, MXNet, and Caffe as backends. It can pull the data out of Spark data frames, have it be resident in the internal H2O data frames, and then it uses these popular frameworks as backend. So that's another way, if you have Spark applications, H2O integrates very tightly and very well with Spark through an interface called Sparkling Water. So it takes a village. There's an interesting set of applications, and now I'm shifting gears. In addition to having GPUs accelerate deep learning, there are GPU-accelerated applications for data analytics. There are some notable GPU-accelerated database companies that I'd like to call out, like Mapt and Kinetica and BlazingDB. There's some visualization packages. Graphistry is a notable one. And so what's happening is these GPU-accelerated applications are starting to be able to nucleate into the Spark ecosystem. So we have a vision of a GPU-accelerated data analytics Lambda architecture where you can do deep learning in a Spark context by the methods I just showed you. And you can also do accelerated SQL queries and other data analytics, all by pulling data from Hadoop into Spark and then into these other packages. And so let me give you an example of one of these. This is a 1-minute video from the company Mapt, and this is the famous taxi cab data set. And so what it is, I'm going to start the video.
Now let's zoom into the Lower East Side. Here on the time histogram,
it's over 1 billion records, and I'm going to talk to it, so I will mute that. And so this is over 1 billion records, and you see they're geospatial in time. It's the trajectory of the taxi cab in time and the pickup and drop off. And so what you can do is it's been spatially joined with the locations of all the stores in Manhattan. So you have this time of day and day of week matrix, and you can see where drop-offs happen. In the morning, they happen at Starbucks. People go to bank in the afternoon. You can see there's a periodicity that's daily on the taxi cab drop-offs. And what's really interesting is you can do sort of ad hoc data analytics. None of this is indexed. It's all these are all queries on over 1 billion records done in real time. And all this geospatial data, which has been joined with the store data, is resident in GPU RAM. And so what's interesting is you can say, for example, let me find the locations of the Hyatt Hotel. Looks like it's stopped running. Sorry, it's running slowly. Probably should have restarted my computer so there was less resident memory. But anyway, I'll just explain briefly what this will show if it keeps running is you look at the locations of the Hyatt Hotel, and turns out there are 5 in Manhattan. And you can actually show that the drop-offs to the Hyatt Hotel chain has some sort of visual correlation with the stock chart of the Hyatt. That's very anecdotal, but hedge funds are using applications like these to do data analytics, to find investment hypothesis and to test them and to get ideas for factor models that would generate alpha. I'll actually come back to this in a second. There's another interesting initiative that's just been announced at our GTC Technology Conference in NVIDIA called Go AI. It's GPU Open Analytics Initiative. And what it is that the company Mapt that I just showed you has open sourced its GPU data frame. So that's not a data frame like the Spark RDD or Spark data frame where it's in system memory. This is actually a data frame in GPU memory. And the GPUs typically have 16 gigabytes of memory. If you scale them out, you can get up to hundreds of gigabytes or several terabytes of memory if you were really motivated. And so what Mapt has done is they've open sourced their data frame and also the SQL algorithms to query them. And there's a consortium that's forming, or an initiative that's forming, where H2O, which is a leading open source enterprise machine learning company, and Continuum Analytics have partnered to create an open set of machine learning algorithms. You now have machine learning. You have Continuum Analytics that is going to expose these algorithms via Python APIs. Things like data.table for R and pandas will eventually run, but they'll be running on the data in the GPU data frame. And the idea is that you can do machine learning and you can do data analytics in this data frame, and then using the frameworks off to the side, you can do deep learning. And so it'll be super fast. So we're very excited about this. As you can see, a lot of it's open source with enterprise-grade support. So it's very much in sort of the Spark ideal. And I wanted to show you an example of H2O algorithm. So this is not yet open source, but this is in their enterprise edition. So what this is a DGX1 with 8 GPUs compared to a system of 2 CPUs, and it's building 4,000 machine learning models. And so these are gradient boosted trees being built on US Census data, and what it's predicting is the income. It's 45,000 rows and 10,000 features, 10,000 columns. And so you can see in the time that the CPU has not even built one model yet with the gradient, sorry, this is actually not gradient boosted tree. They can do that too. This is a GLM, a generalized linear model. You see that very quickly, I'm going to move on, but it's built about 2,500 different models, and it's doing hyperparameter sweeps. And the green is high accuracy, the red is lower accuracy. And by the end of this, if I let it go, you would see that the CPU would have basically built one model. So this is actually going to be something that would run off of the GoAI data frame, and you can have multiple applications accessing that data frame, so you don't have the problems with always having to reload the data in the GPU data frame. So we're very excited about that. I think I have 2 more slides. This is an example of an application that GoAI could be used for. And so it's a hedge fund alpha generation workflow where basically they can take tick data, they can put it in the GPU memory, they can take external data, do deep learning on it by the high density systems that I showed you with the standard frameworks, extract metadata, and then put them into machine learning models, do hypothesis testing in the way that I showed you. They can query alternative data like this taxi cab data set. They can do end-to-end machine learning and deep learning models. And all of this data would be resident in the GPU data frame. And you'd be able to write Python programs. You'd be able to do machine learning with H2O algorithms that will eventually be open sourced. And you'll be able to use Mapt to do ad hoc data analysis. So we think that this is very interesting. And there are already some hedge funds that are looking at workflows like this with us. You can do things like extract all kinds of things from satellite and drone imagery with deep learning and merge that into this data frame. And so this is my last slide. So how to scale artificial intelligence and data analytics? There are a number of ways, but we're very excited about the fact that GPUs are revolutionizing the ability to do high-scaled deep learning, but also the fact that there's now this initiative where you can create a memory-resident GPU data frame in this GoAI initiative, and also the fact that you can do deep learning in the Spark grader ecosystem, and you can use, you can do data analytics, you can do machine learning, and now you can do GPU-accelerated deep learning either in Spark or in a scaled system like this. So there's a lot of options, and GPUs are revolutionizing machine learning, deep learning, and data analytics. Thank you very much.